we have two small balls of mass m connected by a spring and massless rods on a horizontal plane as shown. Find period of small oscillations. So this system is on a horizontal plane. This is a nailed hinge, and these two are massless rods. These two are massless rods, and we have these two balls which are connected by a spring or spring constant K, and there and the unstretched length, the natural length of spring is 2x naught, and we have to find the time period of small oscillations. Now small oscillations here will be of angular nature. Let us say this angle is theta, this angle will also be theta, this is the perpendicular where this distance is h. Now suppose we displace both these balls slightly from their mean position. So I take this to here, let us say this is the final position, and this here, this is the final position, and now spring will be a little stretched in this position. Fine. Now let us see what we can write in the equilibrium position. In the equilibrium position we can write sine theta, is equal to x naught divided by L. Now if I differentiate this equation, see x naught is the length, half length of this spring. If I differentiate this equation, I have cos theta d theta is equal to dx naught by L. So dx naught is equal to L cos theta d theta. Now cos theta in the equilibrium condition will be equal to h upon L. So I can write this to be L into h upon L d theta. So this is equal to h d theta. Now what is dx naught, which we have found to be equal to h d theta? Dx naught is the change in half length. So this distance, this will be dx naught, and similarly here this distance, this will be dx naught. So the stretch in the spring length is equal to 2 dx naught. Now this rod here, this is a massless rod, and let us say this is some angle, let us say d theta. Now because of this finite displacement, now this is d theta, and we have found this relationship to be delta x is equal to 2 dx naught, which is equal to 2h d theta. Now let us see what is the torque acting on this rod. Because of the spring force? The spring force will be like this. So on this particle the spring force is 2k dx naught. 2k dx naught is the spring force, and I have this diagram to be like this. This angle is theta, and the component of this force perpendicular to the rod. Now this angle will also be theta. This force is 2k dx naught. The component of this force, spring force, perpendicular to the rod will be 2k dx naught cos theta. So torque acting on the particle, torque acting on this rod, this is equal to 2k dx naught cos theta, and 2k dx naught cos theta, that is the component of force perpendicular to the rod, multiplied by L, and this should be equal to I alpha. Now this implies that see, we have 2k dx naught we have found to be hd theta. hd theta. Cos theta from the equilibrium condition, cos theta is equal to h upon L. Cos theta is equal to h upon L into L is equal to I alpha for this rod and particle system. For this rod and particle system, the moment of inertia about this axis of rotation, this is a massless rod and this is a particle. So moment of inertia for this rod particle system is ml square. So this is equal to ml square alpha. So I cancel these. So I have equation 2k h square upon ml square, 2k h square upon ml square d theta is equal to alpha. Implies that alpha is equal to 2k h square ml square d theta. Now negative sign is implied because the angular displacement was anti-clockwise and the torque is clockwise. Since the angular displacement was anti-clockwise and the torque is clockwise, the negative sign is implicit here. So I can easily write minus sign here. That is implicit here. And we recognize that this is SHM equation and this will be equal to omega square. So omega square is equal to 2k h square upon ml square. So omega is equal to root of 2k h square upon ml square. Time period will be equal to 2 pi over omega, so 2 pi root of ml square upon 2k h square. So this is the time period of small oscillations.